these are basically insulin dependent, and some of them aren't. Okay, but in other words, the insulin dependent ones are a lot of the majority of the tissues. But what about red blood cells? Do you want an insulin dependent thing to get glucose into them?
No.
Because how long would you survive if you were diabetic? Not very long. Okay, so they're, the ones that go to the majority of the tissues are insulin dependent, but those to go to those critical tissues that you couldn't live very long if they didn't get energy, don't have to have insulin to pull the stuff in usually. Okay. Now, as far as the brain, the liver, the red blood cells, and the white blood cells, they have gluts that really aren't insulin dependent. As far as the heart is concerned, it doesn't take up that much glucose anyway, so you don't have to worry too much about that one. Okay. Now, as far as insulin, once it gets into the liver, it's going to stimulate the liver to store glucose in the form of glycogen. Now, but if the blood levels of glucose are low, is it going to do this, or is it going to utilize it for other tissue? So it depends on what your supply of glucose is, as whether or not you're going to get glycogenesis going on. Okay. A large fraction of glucose absorbed from the small intestine is going to be immediately taken up by the hepatocytes. And what facilitates this immediate uptake? I mean, as far as anatomical. Where do the mesenteric veins are what absorb the stuff from the guts, right? What do they empty into? The portal vein. What's the portal vein go to? It goes to the liver. Okay. The vena cava does not drain it out there. The vena cava drains it from the hepatic vein which comes out. So what does that tell you about the stuff you eat? What organ is going to get it first? The liver. And that's good because the liver's the mastermind. It decides, well, I need to make, I don't need to make any glycogen because my tissues are begging for more glucose. Okay, and so it will regulate that. Okay. Now, if you, basically don't need the glucose to be utilized right away, that's when it's going to be stored as glycogen. Okay. Now, in the absence of insulin, glycogen synthesis in the liver will cease. And the enzymes that are responsible for breakdown of glycogen become active. In other words, what's the liver sensing? We don't have enough glucose, right? And why is it sensing that? Because what insulin is necessary, to regulate blood glucose levels. So if we don't have enough insulin, the liver is going to say, well, that probably means we don't have enough glucose out there, so I better make some. Is that going to be necessary in the situation? Not necessarily. You can have hyperglycemia. I mean, in other words, if you have diabetes mellitus, does your body control the glucose, or do you basically have to do it? You have to do it because the body tissues get fooled. Okay? All right, well, if you look at the lipid, as far as insulin is concerned, it promotes the synthesis of fatty acids in the liver. And remember, fatty acids, they can be stored as the triglycerides, these type of things. Fatty acids are one of the main storage forms for energy in the body. But insulin will increase the activity of your lipoprotein lipase that's in capillary endothelium and extrahepatic tissue, and that's going to get increased movement of fatty acids into your adipose tissue. And so basically it's going to inhibit the breakdown of fat in adipose tissue by inhibiting the intracellular lipase that does this. In other words, what insulin wants to do is to build up your fatty acid. Now, if you don't have the insulin, what's going to happen to that? Is that mechanism probably going to be reversed? You're going to start breaking down the fatty acids because the body's going to interpret it as needing more glucose. And so you're going to go to the liver and you're going to synthesize that into glucose. So it's a very, if you mess up one part of that mechanism, you can cause all kinds of problems as far as the metabolic state, as far as the body is concerned. But if you know insulin is going to promote glycogen synthesis, okay? It's going to promote your glucose, of course, to go into your cells. It's going to promote building up of your fatty acids and your fats and stuff. So without the insulin receptor, without insulin, that's all going to reverse, right? What's going to happen to glycogen? It's going to be broken down. What's going to happen to fat? It's going to be broken down. As you can see, it's a control mechanism. What's the overall aim of all those mechanisms to do? To maintain what? Maintain blood glucose levels, to maintain normal metabolic processes and stuff. Okay. Well, in addition to the effects of insulin to cause entry of glucose into your various cells, again, it also stimulates the uptake of amino acids. And so this is basically an overall anabolic effect, because what do cells need to maintain their structure? Amino acids and stuff.
Is it building up fatty acids for future gluconeogenesis?
Yeah, the question is it building up fatty acids for future gluconeogenesis? Yes, it's a protective mechanism so that they're available. Okay? And basically it's going to promote or increase the permeability of many cells to potassium, magnesium, and phosphate ions. And basically the effect of potassium is kind of clinically important in insulin. In other words, can hyperkalemia be dangerous? What does hyperkalemia cause if it gets high enough? Okay, it's going to cause basically cardiac arrest, right? Is that compatible with longevity usually? So what's one of the treatments?
We give it insulin and
Right, the emergency treatment, because what do you want to do? Emergently, you're not going to lower that potassium. The emergency is to prevent it from going into those tissues where it's going to cause a problem. Okay? And so what you can do is to give glucose and insulin. And what that does is it basically will take that blood potassium into cells which have insulin receptors. What about the heart? Does it have any? It doesn't have it, so it protects the heart. It's not going to hurt to have a little bit of that potassium going into the liver and some other tissues, but it's going to hurt if it goes into the heart. Okay, and so that's it's not going to take care of the situation. What it's doing right then is just protecting the heart to actually lower that potassium even further. Then then you've got to give a little more insulin glucose with that to protect it. Okay? Now calcium can protect the heart initially. Alright? Because calcium and potassium compete with each other for uptake by the heart. Calcium wins. But you've got to be careful when you're doing that. It's not going to do anything to your blood potassium levels. And if I give too much calcium, can I cause some other heart problems? What does hypercalcemia do to the heart? Tachycardia. Now, it might be a little bit better than bradycardia, but if you get overboard, you can go the other way. So that's, in other words, what we do is we give it at the dose that only lasts about 20 minutes. And that gives us time to give insulin and glucose to basically take that potassium out of the blood. Okay? So we have to work that together. So in other words, what's pharmacology based upon? What are drug pharmacology based upon? Your physiology, your normal mechanisms. And what's the best way to treat anything? Physiologically, right? That's when you do it, right? Hey, what's glucagon? What cells did it come from? The alpha cells, right? Alpha for glucagon, beta for insulin. What comes first? G or I? What comes first in the alphabet? G or I? G. What comes first in the Greek alphabet? Alpha or beta? Alpha. So alpha, glucagon, beta, insulin. Okay, makes sense? And it is a linear protein synthesized by your alpha cells. It's about 29 amino acids in length, and basically there's very, very little differentiation between species as far as the sequence of these amino acids. It's structurally related to that secretin family of peptide hormones. That secretin, do y'all know where secretin comes from? Also comes from the bile duct and stuff like that, from the pancreatic duct and everything. What's its function?
This makes nitric acid.
It's secrete bicarb in exchange for chloride. Okay, to increase the pH of your intestines so you don't destroy your acids, right? Now, it's synthesized as proglucagon, just like all your other peptide hormones as far as pro is concerned. And then it is proteolytically cleaved to different areas to give you the final hormone. And your proglucagon can be secreted by cells in the wall of the duodenum and the stomach. The duodenum is called glycetin, and the stomach is called enteroglucagon. And basically, this is pro. When it gets into the stomach, the proteases cleave off the thing and make it into an active glucagon. Okay? Now, as far as its release, it's going to be regulated by your plasma glucose levels. What kind of levels do you have to get glucagon to be released? Low glucose levels, right? Because what's glucagon's main function? To raise blood glucose, okay? And it's going to cause a decreased secretion in low glucose levels. We're going to cause, you know, the glucose. In other words, blood glucose goes up. What should happen to glucagon? How does glucose do that? Goes into the alpha cells, right? What is necessary for that glucose to get into the alpha cells? They have insulin receptors. Insulin is necessary. Okay, to get them in there. So, can you see how if I've got an animal that's diabetic, what about my insulin levels? Very low. So what's my blood glucose going to do? Build up. But what are the alpha cells? What's the problem there? They don't have that insulin receptor because this glucose has to go into them to tell them, hey, you've got too much glucose. Okay? Or you don't have enough glucose. If you have too much glucose, they're not going to secrete. What if you don't have enough glucose? They're going to secrete. Now the problem is, if the insulin's not there, are they ever going to detect that there's too much glucose out there? Or are they going to say, oh my heavens, the glucose is too low. Let's get out there and get more glucose. Is that going to help that animal? Is that going to aggravate it? What's going to happen to your blood glucose? Higher and higher. Okay? That can cause problems with it. Okay? And so that's one of the things that they didn't really recognize that until a few years ago. Okay, couldn't quite understand why, you know, they were seeing all this glucagon being released or not being released and stuff like this. They couldn't figure it out until lately. Okay. Now, two other conditions can trigger glucagon secretion: elevated blood levels of amino acids. In other words, if you eat a nice protein-rich meal, you absorb all these amino acids, glucagon will foster the conversion of those excess amino acids to glucose because they enhance gluconeogenesis by the liver. So since high blood levels of amino acids will also stimulate insulin release, basically this would be a situation in where you're getting insulin, you know, the glucagon's causing the glucose to be produced, insulin's causing the glucose to go in the tissues it's supposed to go to. And so that's one of the mechanisms. It's one of the reasons it gives you a very quick energy burst compared to some other things. Because what do a lot of athletes and things eat as far as their meals are concerned? And they also eat a bunch of proteins and stuff in there. And this is one of the reasons they do that, because it gives this burst of energy and everything, okay? Now, exercise, as far as in this case, it's not clear whether the actual stimulus is exercise or the accompanying depletion of glucose. Now, I've told you that too much exercise can kill you, but you know, a little bit of exercise is beneficial, okay? And so, as far as you're doing, if you're exercising, what do you need as a source of energy? You gotta have the glucose and stuff as a source of energy. And so, what do you think the insulin level is going to be? No, if you're exercising, you're going to need the glucose. So what does your energy? What does your insulin level have to be? It has to be high. But if you overdo it, can you deplete the blood too much? Can you go into hypoglycemic shock? So can the exercise kill you? Yeah. Now I'm not saying don't exercise. I just said use your brain. You know, do it. You know, like you're supposed to. Unless you aren't there doing a 40-mile marathon. You know, you don't want to overdo it, right? Okay, so here are just some factors that affect, either stimulate or inhibit glucagon secretion. The major one, of course, is increased blood glucose. But as we said, amino acids can do it. Also, your epinephrine, norepinephrine can do it, because basically what that's trying to do is to raise the blood glucose so it can go into the brain where you need it, this type of thing. Some of your gastric enzymes and stuff will do it because they're preparing the body for, glucagon coming in and getting dropped glucose coming in and getting dropped real rapidly by the insulin, so the glucagon's got to be ready to moderate that. Okay, so that they can work synergistically. Inhibitors, of course, the increased blood glucose will inhibit it, somatostatin will inhibit it, and fatty acids will inhibit it. Remember, amino acids and fatty acids will stimulate some of your insulin. Fatty acids inhibit glucagon, amino acids stimulate glucagon. Okay, as far as going in that action. Now, as far as where's the metabolism of glucagon going to take place? It's going to take place in the liver and kidneys. And the half-life of endogenous glucagon is about 5 minutes. So again, you see that these are such powerful hormones, they have to be very closely regulated. And that's why they don't hang around like that. Now, the major role of glucagon is maintain normal concentrations of glucose in the blood. And so it's basically, remember those antagonistic groups of hormones we talked about with mechanisms of endocrine control? This is an example of that. Because what's insulin going to do to blood glucose? All right, what's glucagon going to do to blood glucose? Raise it, so they work antagonistically like that. Okay. Now, it exerts control over two very pivotal metabolic pathways in the liver, and it leads to basically leads that organ to dispense glucose to the rest of the body. In other words, the liver gets the glucose from the meal, right? And then glucagon comes in there and says, hey, we need to take this to the tissues, and so activate the metabolic pathways which excrete this glucose from the liver into the blood. Basically go where it needs to go. It's going to stimulate the breakdown of the glycogen also that's stored in the liver. It's going to activate, as we say, hepatic gluconeogenesis. And so basically it's going to promote lipolysis of adipose tissue. That's going to give you a release of serum fatty acids, and those fatty acids can then be taken up, make glucose out of them, or they could also be used for energy if necessary. Okay? So you can see it's the opposite effects of what your insulin is doing in most instances. Okay? Now, pancreatic somatostatin. Maybe remember that one that we had up in the pituitary? It's the same structure as that produced by the pituitary. And it's a 14 amino acid peptide as produced by the delta cells in the pancreatic islets as far as the endocrine pancreas is concerned. And things which will stimulate its synthesis and secretion would be epinephrine and norepinephrine, acetylcholine, glucagon, increased blood concentrations of glucose and amino acids. In other words, it's regulatory. If we got too high of our concentrations of blood glucose, okay, what is that going to basically stimulate the secretion of? If you got too much blood glucose, what does that mean? You probably may have too much of glucagon. So what's it going to do to the production of glucagon? Inhibit it. If you don't have enough blood glucose, what is that telling the body it's got too much of? Probably insulin. And so that's how it regulates. Unfortunately, sometimes this little brain gets befuddled up there, and it doesn't quite do what it's supposed to do, and that's when you get all kinds of problems as far as the body is concerned. Has a half-life of about 5 minutes. Again, it's mainly metabolized by the liver and kidney. So that would be a hard multiple choice question. What is it? What organ responsible for the metabolism of any of those? 5 different questions, using different hormones, and all the same answer, right? Okay. Now, as far as what it can do, it inhibits the secretion, as we say, of all your other pancreatic hormones. It creates an inhibitory effect. The greatest is upon glucagon. But it also inhibits your digestive proteases. It decreases GI tract motility and secretory activity. And if you don't have that, what happens to absorption of nutrients and stuff? It inhibits that. So in other words, what do you think a tumor that's producing somatostatin? You think that's going to be very compatible with longevity? No. It causes all kinds of problems. They at one time thought about using somatostatin as a weight loss thing. And they found out with their laboratory animals that it wasn't the best idea in the world. Because one problem is, if you're not got the motility, and you basically are still going to get some acid coming out there, and that acid sits around in the GI tract, what are you going to get? Ulcers and everything else. That's the problem we have with this. Now, so as far as your regulation of blood glucose levels, what's the difference between the GI tract absorption of glucose and ruminants and simple stomach animals? What's the difference? Well, no, but do ruminants absorb much glucose?
No.
No, the fermentation processes and everything make it into ketotic acids and propionic acids. So the ruminant doesn't absorb very small amounts of glucose from the gut. Main thing is the source of propionic acid. What happens to that propionic acid? Take it to the liver, and what's the liver make out of it? Glucose. Okay? So if I ask you, if I have hepatic insufficiency, which species is going to develop hypoglycemia first? And I gave you A is dog, B is cat, C is horse, D is cow, and E is pig. The cow, because if the liver is not able to take that propionic acid and make it into glucose, what's going to happen to the blood glucose levels in that animal? then, well, they never got up there to begin with, probably. Okay, whereas other species, they absorb glucose, so then when that level drops, then the liver comes into play. So it's going to be a while before you see severe hypoglycemia with those animals that absorb glucose intact. Does that make sense? And again, what species is going to develop hypoglycemia after a longer period of time? Of those ones I just gave you? I hear a dog, I hear horse. How many for horse? How many for dog? Cat? In other words, which species will take longer to develop hypoglycememia with liver function failure?
Horse.
The cat?
Let's go with cat.
Why do Europeans love horse meat? It's sweet. Why is horse meat sweet? Because there's all kinds of glycogen, excessive levels of glycogen in the muscle of horses. Okay? And so when push comes to shove, if the liver can't make the glucose, the muscle can to a certain extent break down that glycogen, but it's limited. That's why it's not going to be that way forever. Okay, after a few days, then you'll start to see decreased blood glucose in those animals. Okay? Anybody here eating horse meat?
Not yet.
I ate some, when my husband and I went to Switzerland one time, I had some, but it didn't taste any different to me. Yes, sir.
I think it'll taste good.
Can't hear you.
You have to go for it.
Yeah, bison have more glycogen in their muscle too. Okay. And they kind of bred them for that. Get that, okay? Now, as far as the, pardon me, in your simple stomach animals, as we say, ingestion of your carbohydrates and fat